Today we're going to talk about what a mineral is. Minerals are naturally occurring, inorganic, solid at room temperature. They have a regular crystal structure and a defined chemical composition. So let's break down this definition a little more. First of all, they are naturally occurring. An example of this that humans can synthesize naturally occurring minerals is diamond. So diamond has this characteristic kind of tetrahedral structure, but we can also synthesize diamonds in the lab in much shorter time than it takes in nature. And if you were just to look at the structure of the diamonds, you wouldn't be able to tell the difference. But because it is man-made, we don't necessarily consider it a mineral by definition. Humans have been making a lot of minerals, hundreds of thousands of man-made or man-mediated minerals since the Industrial Revolution. We have anything from bricks to ceramics and porcelain to crystals in batteries and man-made minerals and magnets that we use, and also lots of things in our cell phone that are man-made, but that have the characteristic properties of minerals. But since they are man-made, they're not necessarily considered minerals by definition. I find it really interesting to think about how we are changing the chemical composition of the earth because of the minerals that we are making synthetically. There are also other types of man-mediated minerals that are being created through natural processes, such as brass that might come from a shipwreck that interacts with the ocean floor to create new kinds of minerals, or unusual humidity or fires that happen in a mine might create new types of minerals in the walls of the mine. So I think it's just something interesting to think about how we are just changing the composition of the earth. So the second part of the definition is that minerals are inorganic. That means that they don't have this characteristic carbon-hydrogen bond that is found in living organisms. But this part of the definition can be a little bit tricky. For example, we have calcite, which is made of calcium carbonate. And the calcium carbonate comes from living organisms. The shells and exoskeleton types of structures, like in sand dollars, clams, and starfish and corals, they all contain calcium carbonate. And so the definition can be refined to say that calcium carbonate coming from living organisms can be considered minerals after they have gone through processes like diagenesis or being formed into rocks through natural processes. Another example of this is diatomaceous earth. So diatoms are tiny microscopic creatures like algae that have silicate shells that look like glass. They're very beautiful. And they can form diatomaceous earth after they have died, and then their silicate shells kind of go through natural processes. This is an example of diatomaceous earth that can break up into powder. So other kinds of minerals that are formed from silicate shells of diatoms are quartz. Quartz is made of silicon dioxide. So the silicon that is in these kinds of quartz here, we have different colors of quartz: tangerine quartz, smoky quartz, rose quartz, and these are all made of silicon dioxide, which once was part of the cell walls of these diatoms. So the third part of the definition is that it is solid at room temperature. So this part is pretty straightforward, but it's important because it excludes things like water and mercury that are not solid at room temperature. So the fourth part of the definition is that it has a regular crystal structure. As we can see, from this model of sodium chloride, it's a model of halite, which is basically table salt. You have it at your dinner table every day. And you can see that it has a crystal structure repeating patterns of sodium and chlorine. And what you can notice is that we have a cleavage at 3 planes, so 1, 2, and 3, all at 90-degree angles. And you can see how the macroscopic structure of halite can reflect its molecular structure, or ionic compound structure here, because it can form almost like perfect cubes. This example is calcite. Calcite is calcium carbonate. So if we look at a model of its molecular structure here, you can see how it would form these angles. Characteristic angles of calcite are a 78-degree and 102-degree angle, kind of like a rhombus. And if you look at its molecular structure, you can see how that form can be reflected in its macroscopic scale. Another example is quartz. Again, quartz is made of silicon dioxide, and it forms this kind of a structure with silicon and oxygens. And you can also see how this irregular crystal structure can be reflected in the macroscopic structure as well. So this is silicon dioxide. We also have an example of obsidian. Now, obsidian is not really considered a mineral. We call it a mineraloid because it doesn't have a crystal structure. And so you can see that in the way that it fractures or breaks, it creates these curved conchoidal fractures that look irregular, and that is due to its irregular crystal structure, which is why it's not necessarily considered a mineral. It's more of a mineraloid. Okay, so finally, minerals have a defined chemical composition. So if you remember back in chemistry class, you know that atoms can bond together and share electrons. There's different ways that they form bonds. So one is an ionic bond like this, sodium and chlorine, which they're two ions that are oppositely charged, and they form kind of like this attractive magnetic bond. And so that's an example of a defined chemical composition in halite. There's also covalent bonds. They're sharing electrons, like in calcium carbonate between the calcium, carbons, and oxygens. Another example, as I mentioned before, that silicon dioxide is what makes up quartz. And so these are forming bonds between the silicon and the oxygens. So there's one silicon for every 2 oxygens, and that is a defined chemical composition throughout the whole mineral of quartz. Sometimes minerals can have different elements in their structure depending on what was available at the time that they were forming. So this olivine could be made of either magnesium or iron, just depending on its environment as it was formed. But throughout the whole mineral, it would have the same structure, depending on what element it is. Sometimes different elements can be part of a mineral structure and create a very interesting property called fluorescence. So what that does is that when it's under an ultraviolet or black light, it will absorb that wavelength of light and then emit light at a different wavelength, causing it to look like a different color and look like it's glowing as well. So we'll show some examples of that here. So in conclusion, a mineral is naturally occurring, it's inorganic, it is solid at room temperature, it has a repeating crystal pattern, and a definite chemical composition. It's helpful to know the definition of properties of minerals and how to identify them in order to identify rocks. So that's what we're going to practice in a rock identification lab, which I will explain in another video. This poem is by Maya Anthony, and it's a poem about rocks and minerals, and she equates them to notes in a grand symphony that narrates the story of our planet. In the orchestra of Earth, rocks play their part, holding memories close to its heart. Minerals chime in with colors so bright. Together they weave the world's ambient light. Limestone and marble, garnet and gold, each with a tale waiting to be told. Feldspar sparkles and sapphire sings. In the symphony nature brings. From cavern deep to peak's snow kiss, rocks and minerals coexist in bliss, for in their union melodies hone a timeless symphony set in stone.